Welcome. This video derives the time domain response of a series RC circuit to a sinusoidal steady-state input voltage. The sinusoidal driving signal, cosine-omega-t in this example, is in steady state. There are no transients. Because the circuit is linear, we know that the circuit response functions will also be sinusoidal signals with the same frequency omega as the input driving signal. Here in this video, we are deriving the current response. We only need to solve for the particular solution of the non-homogeneous differential equation. We don't need to solve the homogeneous or complementary equation corresponding to transient response.
Let's start with an outline overview of the derivation process before we delve into all the detailed derivation steps. The equation numbers used here in the outline come from the detailed steps that follow.
First, we use Kirchhoff's voltage law, KVL, to generate the differential equation shown in equation 8 for the series RC circuit. Next, we choose a likely solution form based on the type of input signal. The A and B in equation 9 are the undetermined coefficients. After solving for A and B and substituting them into the differential equation 9, we get the time domain solution for the loop current I of t shown in equation 37.
But equations 9 and 37 are written in terms of both sine and cosine. We want a current solution function just in terms of cosine, like equation 38.
We can express the differential equation solution in terms of only cosine by using a trigonometric identity for the sum of two angles in equation 41. Combining equation 41 with equation 9, shown in equation 42, gives us A and B expressed in terms of magnitude m and angle phi in equations 43 and 44. Using equations 43 and 44, we can derive the tangent of phi. Then, taking the arctangent, we solve for phi in equation 50. Next, to solve for the current magnitude m, we apply the Pythagorean Theorem for sine and cosine in equation 51 to generate expressions for A and B in terms of m and phi in equations 45 and 46. Square equations 45 and 46, sum them, then factor out m squared, and solve for m.
Sinusoidal steady state connects time domain response to steady state linear frequency domain response, where the use of phasors requires sinusoidal steady state. The phasors used for sinusoidal steady state frequency response are described in a different video in this series.
Time domain solution of circuit differential equations, shown in yellow highlight, is very general. Phasor domain analysis is limited to sinusoidal steady-state signals in linear circuits. This video derives the time domain solution highlighted in yellow.
Now we are starting the detailed derivation steps.
The first step in the analysis of this RC low-pass filter circuit is to write Kirchhoff's voltage law around the loop, starting at the voltage source represented by V sub s in the schematic. Summing the voltages around the loop clockwise gives us equation 1. Move the source term V sub s to the right side in equation 2. Then, in equation 3, insert the cosine function for V sub s of t. Capital V sub s is the amplitude of the time domain input voltage V sub s of t. We want to replace the voltage terms in equation 3 with expression in terms of the current I of t. The branch relationship for a resistor is Ohm's law, shown in equation 4. The equation for the voltage across the capacitor is shown in equation 5. Substitute these two branch relationship equations, equations 4 and 5, into the KVL equation 3, resulting in equation 6.
We will solve equation 6 for the RC loop current I of t.
Next, we differentiate both sides of equation 6 with respect to time, resulting in equation 7. Divide both sides of equation 7 by the resistance R, giving us equation 8.
Equation 8 is the linear, first-order, ordinary differential equation for loop current I of t.
We will use a differential equation solution approach called the method of undetermined coefficients. Since the input voltage is a sinusoid and the circuit is linear, we know that the solution will also be a sinusoid. We choose a general sinusoidal form shown in equation 9. A and B are the coefficients that need to be determined.
After solving for A and B, we will then further refine the solution into the cosine function form shown in equation 10.
Next, let's try out our proposed solution current form, equation 9. First, take the derivative of equation 9, shown in equation 11 as I prime of t. Then substitute for both I of t and I prime of t using equations 9 and 11 into our RC differential equation in equation 8. The result of the substitution is equation 12. We can multiply out the 1 over RC term right in the middle of equation 12, moving the 1 over RC term inside the brackets, resulting in equation 13. Move terms around in equation 13 so that the two sine terms are next to each other and the cosine terms are next to each other, as shown in equation 14. There is still a sine term on the right side of equation 14. Move that sine term to the other side of the equal sign so that now all three sine terms are adjacent to one another in equation 15. Next, in equation 15, factor out the sine and cosine terms to obtain equation 16.
We know that equation 16 is valid for all values of time t. We will use this knowledge to generate two different equations, which we will then solve simultaneously for A and B.
For the first simultaneous equation, choose time t equals 0. At time t equals 0, the sine of omega t equals 0, so the entire sine term in equation 16 becomes 0 in equation 17 and 18. Cosine of 0 equals 1, which is also indicated in equation 17. The resulting equation 18 is the first of two simultaneous equations that we will use to solve for A and B. For the second simultaneous equation, go back to equation 16. Now set time t equal to pi over 2 omega. This makes omega times t equal to pi over 2, 90 degrees, where cosine equals 0 and sine equals 1. We see the sine term equal to 1 in equation 19. The cosine term equals 0 in equation 19. Simplifying equation 19, dropping the 0 term and removing brackets, gives us equation 20. Move terms in equation 20 to obtain equation 21, which is the second of two simultaneous equations that we will use to solve for A and B.
Simultaneous solution of equations 18 and 21 will determine the coefficients A and B in the RC circuit differential equation.
Now we are starting the simultaneous solution for A and B. We start with equation 18, which we solve for B in equation 22.
Of course, equation 22 still contains A.
Substitute equation 22 into equation 21. The resulting equation 23 no longer contains B. Simplify equation 23, removing the brackets, resulting in equation 24. From the right side of equation 24, factor out A to obtain equation 25.
We're getting there. We just need some algebraic steps to get our desired expression for A.
Divide both sides of equation 25 by the quantity in parentheses on the right-hand side so that we isolate A as shown in equation 26. Next, multiply the numerator and denominator of the right side of equation 26 by resistance R to obtain equation 27.
We still have some algebra steps to go.
Divide by omega on the right-hand side of equation 27 to obtain equation 28. Distribute the omega term in the denominator of equation 28 into the brackets. This gives us an omega over omega term in equation 29. Simplify that omega over omega term to become 1 inside the brackets in equation 30. Next, we distribute the r squared term in the denominator of equation 30 into the brackets, resulting in equation 31, where the 1 becomes r squared and an r squared term cancels. Equation 32 just adds brackets and rewrites the squaring in the denominator. We're done with this solution for the coefficient A, which is ready to be plugged into equation 9, the proposed solution form for the RC circuit current. From equation 32, equation 33 is just a very slightly different notation in the denominator.
We have completed the first step in the simultaneous solution steps for determining the coefficients A and B. Next, we will go back and solve for B.
Starting the second part of the simultaneous equation solution, we go back to equation 22 for B expressed in terms of A. Reformat equation 22 for visual clarity in equation 34. Substitute equation 33, the solution for A, into equation 34 to obtain equation 35 for B, now no longer expressed in terms of A.
Now we have an expression for B in terms of circuit parameters.
Rearrange equation 35. Put the minus sign into the numerator. Cancel the R term between the numerator and denominator. Combine the two denominators using parentheses. The result is equation 36.
Equation 36 is a solution for the coefficient B from the original proposed solution form in equation 9.
The two simultaneous equations are solved. With equations 36 and 33, we have expressions for both A and B in terms of circuit parameters. Now substitute equations 36 and 33 into equation 9 to obtain equation 37, the solution for the RC circuit current I of t in terms of both sine and cosine.
But we want a current solution function just in terms of cosine, like equation 38.
Yes, we want to express equation 37 in terms of cosine, magnitude m, and angle phi, as shown in equation 38.
How do we do that?
To start with, we will make use of equation 39, which conveniently expresses sine and cosine terms on the right side of equation 39 in terms of one cosine term on the left side of equation 39. To make use of equation 39, set alpha in equation 39 equal to phi from equation 38. Set beta in equation 39 equal to omega t from equations 9 and 37. Substitute these new terms for alpha and beta into equation 39 to obtain equation 40. Rearrange terms on the right-hand side of equation 40 and multiply the entire equation 40 by capital M to obtain equation 41. Now the left-hand side of equation 41 looks like equation 38, the cosine format we want. Remembering that equation 41 also equals current I of t, combine equation 41 with equation 9, containing the A and B terms. The result is equation 42. We can see in equation 42, comparing terms on both sides of the equation, that A equals m times cosine phi, shown in equation 43. B equals minus m times sine phi, shown in equation 44. Next, we'll combine these new equations 43 and 44 with our equations 33 and 36 for A and B in terms of circuit parameters. Substitute equation 43 into equation 33 to obtain equation 45. Substitute equation 44 into equation 36 to obtain equation 46.
From this information, we want to get expressions for both the m and phi terms in equation 38.
Starting with phi, divide equation 46 by equation 45 to get an expression for tangent phi in equation 47.
Sine divided by cosine equals tangent, leading us soon to tangent phi. From tangent phi, we will calculate phi.
For visual clarity, reformat equation 47 to obtain equation 48. Cancel like terms in equation 48. The terms in parentheses are the same in the numerator and in the denominator. There are also v sub s terms both in the numerator and in the denominator. The result of the cancellations in equation 48 is the expression for the tangent of phi shown in equation 49. Take the arctangent of equation 49, providing an expression for phi in equation 50.
This expression for phi from equation 50 will soon go into equation 38.
Now that we have an expression for phi in equation 50, we need to solve for m in terms of the RC circuit parameters. To solve for m, we will make use of the sine and cosine version of the Pythagorean Theorem in equation 51. Equation 51 relates to the more general form of the Pythagorean Theorem shown in equation 52. The hypotenuse of the triangle C in equation 52 equals 1 in equation 51. Remember that the radius of the unit circle equals 1. Square equation 45 and add that to the square of equation 46, resulting in equation 53. Factor out the m squared term on the left-hand side of equation 53 to obtain equation 54. From equation 51, the sine and cosine version of the Pythagorean theorem, we know that the bracketed term on the left-hand side of equation 54 equals 1. Applying equation 51 to equation 54 gives us just the m squared term on the left-hand side of equation 55.
We're getting close, but we have more algebra steps to go.
We can simplify equation 55 by moving the square terms on the quantities in large brackets to the inside of the brackets, resulting in equation 56, which no longer has those larger brackets. Reformat equation 56 by moving the omega-c quantity squared term from the denominator into its own expression as 1 over omega-c squared in the numerator. Also separate the r squared term from the rest of the right-hand term on the right-hand side of equation 56. The result is equation 57. Notice how equation 57 has two identical denominator terms in adjacent sums. We can factor out that common term in equation 57 to obtain equation 58, which is now a single term for capital M squared. Cancel like terms in equation 58, resulting in equation 59. Take the square root of equation 59 to obtain equation 60, which is the final expression for m that we need for our overall RC current solution expression. With equation 60 for m and equation 50 for phi, we have all the information we need to express the current in the desired form of equation 38. Substituting equations 60 and 50 into equation 38, we obtain equation 61, the final solution for the sinusoidal steady-state current in the RC low-pass filter circuit from Figure 1.
And now we are finally finished.
Referring back to the time domain solution flowchart featured in the phasor video and shown near the beginning of this video, on slide 7, we see that we have derived the same equation as the one shown in the flowchart. For more technical background and insight on different RC circuit time domain responses, please see this book, First and Second Order Circuits and Equations, available from John Wiley & Sons.
Thank you for watching and learning with us.